Welcome to the lesson on end effectors. Upon completion of this lesson, learners will be able to describe end effectors in robotics, identify different grip styles, different types of grippers and their configurations, identify the difference between prehensile and non-prehensile grippers, and choose the type of end effector based on application. Think of end effectors as the robot's hands. They're the tools attached to the end of a robot's arm that do the actual work. Just like we use our hands to pick things up, move them around, and work with tools, robots use end effectors to interact with objects and perform tasks. Whether it's picking up car parts on an assembly line, handling delicate electronics, or working with specialized tools, end effectors are what make it possible for robots to physically interact with the world around them. They're basically the robot's way of reaching out and touching things, kind of like how we reach out and grab something when we need to move it or work with it. End effectors are also called end-of-arm tooling. End effectors in robotics can be classified into several types. Grippers represent the most common category, designed to grasp and manipulate objects in various ways. Tools form another essential category, which includes devices like welding torches and paint sprayers that enable robots to perform specific manufacturing processes. The third category consists of sensors such as cameras and force sensors, which provide feedback and data collection capabilities, allowing robots to interact more intelligently with their environment and perform tasks with greater precision. These types of end effectors can be used individually or in combination, depending on the specific requirements of the robotic application.
An end effector is the device at the end of a robotic arm, like one of these that you see here. Oftentimes, end effectors consist of some kind of tool. For example, these robots have welding end effectors that allow them to join metal components in the manufacturing process. End effectors can also be used to grab objects and move them from place to place. Collectively, these end effectors are called grippers and come in many different forms. They include two-finger gripper. A two-finger gripper is a passive end effector. This means that it can hold parts but cannot manipulate or actively use them. The two-finger gripper applies a pinching pressure to an object in order to move it. Suction. A suction gripper is another type of passive end effector. It uses a vacuum to adhere to and move objects from place to place. Three-finger gripper. A three-finger gripper is an active end effector. The parts in its grasp can be manipulated or actively used. They are more dexterous than passive end effectors, giving them more precision and the ability to complete fine motor tasks. There are many other types of grippers and end effectors. The type of gripper that is used varies based on the application. One of the most important areas in the design of robotic systems is the design of the end effector. As technology advances and automation becomes even more prevalent in manufacturing, becoming familiar with end effectors and how they are used becomes increasingly important.
This lesson discusses the gripper type end effectors. Let's start by discussing the various gripper styles in industrial robots. Robot grippers are mechanical devices designed to mimic the functionality and dexterity of a human hand. They play a critical role in robotics, especially in tasks that require precision, adaptability, and interaction with diverse objects. These grippers emulate the human hand's ability to grasp, hold, and manipulate objects by incorporating a combination of structural design, motion control, and sensory feedback. There are two grip styles, prehensile gripping and non-prehensile gripping. Prehensile gripping typically involves movements that usually require some sort of thumb. These grips are used for manipulating, rotating, or transporting objects securely. They are often employed for different shaped objects, such as small cylindrical objects or spherical objects. Non-prehensile gripping refers to grips that do not require a thumb. These may involve spreading motions or hooking motions. Let's first discuss prehensile movements. These movements require the use of a thumb. The video will give you an idea of the various prehensile movements. Cylindrical grip involves forming a C shape with your hand, allowing you to grasp cylindrical objects. The wedge between the fingers and the thumb is used to grasp, manipulate, and pick up objects. Spherical grip involves spreading your fingers to create a spherical shape, ideal for holding round objects. It requires at least 3 digits, including the thumb and 1 or 2 other fingers, to enclose the object. Pinch grip utilizes the thumb, middle finger, and index finger for high-precision movements, such as picking up a grain of salt. The object is wedged between the 3 fingers for precise control. Scissor grip involves extending 2 fingers to grasp an object. Here are examples of prehensile movements in EV manufacturing, showing how robots use different gripping techniques for specific tasks. Cylindrical grips are used for battery cell installation, where robots carefully grasp individual cylindrical cells to place them precisely into battery modules. When working with the electric motor assembly, robots typically employ spherical grips to position and install round bearings into motor housings. For more delicate work, pinch grips come into play when placing small electronic components onto circuit boards for battery management systems, abbreviated as BMS. The scissor grip technique is particularly useful for underbody work, allowing robots to reach between components to attach protective shields under the vehicle. Each of these gripping methods is specifically chosen to match the shape, size, and handling requirements of different components. Now that we've discussed prehensile grips, which require the use of a thumb, let's discuss non-prehensile movements. These movements often do not require the use of a thumb to manipulate the object or obstacle being interacted with. As the name suggests, hook movement focuses on hooking onto something, such as a handle or another object. The primary goal is to pull the object, not necessarily rotate it. The image shows a gripper with hook-shaped ends on each finger. This allows the gripper to latch onto thin objects with only one side, eliminating the need to fully close the gripper to manipulate the object. Spread movement involves inserting the gripper and its fingers into an object, such as a cylinder. The fingers then spread out to fill the object, utilizing an internal mechanism to grasp it. This method allows for orientation, rotation, and translation of the object without requiring an outward closing grip with the thumb. It functions similarly to a reverse pinch grip, where 2 fingers are inserted and then spread apart until they connect and latch onto the object. Here are 2 examples of non-prehensile movements in EV manufacturing, where robots manipulate or inspect components without grasping them. In cable routing, robots employ a hook-like end effector to pull wiring harnesses through chassis channels. For battery module inspection tasks, robots utilize a spread movement, where their fingers extend outward to measure gaps between battery cells, similar to spreading your fingers to check the width of a gap. Now let us examine the various gripper types in industrial robots. Here's a high-level overview of the various types of grippers used in robotics. Mechanical grippers feature 2, 3, or 4 finger configurations that can move in parallel or angular motions, capable of both internal and external gripping. Vacuum grippers employ suction cups that create vacuum or suction movement for external gripping only. Pneumatic grippers use 2-finger or tooling jaw configurations that can move in parallel or angular ways, which are suitable for both internal and external gripping applications. Electromechanical or magnetic grippers utilize magnets that create magnetic attraction for external gripping operations. Each type offers distinct advantages for specific applications based on their configuration, movement type, and gripping capability. We will discuss more about these types of grippers and their applications as we proceed through this lesson. Let's look at the first and the most common type of gripper, the mechanical gripper. Mechanical grippers operate through a system of mechanical components working together. They use mechanical linkages and gears to transmit force. The primary actuation comes from electric motors or linear actuators, where a motor drives 2 linear racks that control the opening and closing movements of the fingers. This motion is converted through either rack and pinion systems or cam mechanisms to achieve the desired movement. The gripper fundamentally relies on physical finger movement to grasp objects, with the fingers typically moving in either parallel or angular patterns to secure items effectively. Vacuum grippers operate using a straightforward but effective principle of negative pressure. These grippers create a vacuum through suction cups, using either the Venturi effect or dedicated vacuum pumps to generate the necessary suction force. For successful operation, they require an airtight seal to be formed between the suction cup and the surface of the object being handled. The system can be designed with multiple suction cups that can either work independently or in unison, providing flexibility for different object sizes and shapes. When it's time to release the object, the gripper either removes the vacuum or applies positive pressure, breaking the seal and allowing for controlled release of the item. The image illustrates a simple example of a suction cup and a vacuum gripper before application. As indicated by the arrows, 4 suction cups are positioned to lift the steel plate. Vacuum grippers are extensively used to handle large, flat components like EV battery covers, glass panels, and body parts during assembly and inspection. Next, we have pneumatic grippers. Pneumatic grippers function by harnessing the power of compressed air to operate their gripping mechanism. The system works by using compressed air to drive a piston or bladder mechanism where applied air pressure forces the piston to move, resulting in the opening or closing of the gripper fingers. These grippers come in 2 basic configurations: normally open, which closes when pressurized, or normally closed, which opens when pressurized. The movement is precisely controlled through solenoid valves that regulate the airflow, while pressure regulators ensure that a consistent gripping force is maintained throughout operation. Finally, we have electromechanical grippers, also known as magnetic grippers. Electromechanical or magnetic grippers operate by utilizing electromagnetic coils to generate magnetic fields for object manipulation. When these coils are energized with electrical current, they create a magnetic attraction force capable of holding objects. The system allows for quick activation and deactivation through precise current control, providing rapid response times in operation. However, these grippers are limited to working only with ferromagnetic materials such as steel. The gripping force can be finely adjusted through the regulation of current and voltage supplied to the electromagnetic coils. Let us now look at the selection criteria for grippers as we proceed through this lesson. When selecting a gripper for robotic applications, these key factors must be considered. Material properties influence what type of grip and force you need. Handling speed determines if you need fast-acting grippers like pneumatic ones. Precision needs indicate whether you require high-accuracy grippers with feedback control. Environmental factors like heat, dust, or moisture affect which gripper will last longest. Space limits in your work area might rule out larger gripper types. Cost includes both buying the gripper and running it over time. Maintenance requirements show you how much upkeep the gripper will need. Each factor directly impacts whether the gripper will work well for your specific task. Here's how to match end effectors with specific applications. Vacuum grippers work best for flat, smooth surfaces and delicate materials. They won't damage surfaces, can handle large areas, and spread pressure evenly across the grip surface. Mechanical grippers are ideal for objects that come in different sizes and shapes. Their grip width can be adjusted. They offer variable force control and provide high precision in handling. Pneumatic grippers excel at high-speed repetitive tasks. They activate quickly, are simple to operate, and deliver reliable performance over many cycles. Electromagnetic grippers are the best choice for ferrous materials and heavy parts. They offer quick release capability, won't deform the materials they're handling, and can manage heavy loads effectively. Vacuum or magnetic grippers work well with hot or sensitive materials. They can handle items without direct contact, resist high temperatures, and provide clean operation without contamination. Each of these gripper types serves a specific role based on the material properties and handling requirements. Different types of grippers play specific roles in EV assembly lines. Mechanical grippers handle assembly work like installing interior trim, putting together steering systems, and managing brake components. These grippers are good for tasks that need precise control and varying grip strengths. Vacuum grippers are used for handling large, flat surfaces. They are used for moving sheet metal, placing windshields on the car frame, and positioning roof panels. Their suction-based system allows delicate materials to be handled without leaving marks. Pneumatic grippers use compressed air for tasks that need consistent force, like routing seat harnesses, assembling door handles, and installing light assemblies. They're especially useful in tight spaces where control and reliability are important. Electromechanical grippers, using magnetic forces, are specifically designed for handling steel components. They're used for transferring bulk steel panels, positioning body sides, and handling floor pans. These grippers can quickly grab and release metal parts without physical contact. In summary, end effectors are devices attached to the robot's arms that interact with the environment and perform tasks. These devices can be classified into three main categories: grippers, tools, or sensors. When it comes to gripper functionality, there are two primary movement styles: prehensile and non-prehensile. Based on the specific application requirements, various gripper types can be employed, including mechanical, vacuum, pneumatic, and electromechanical magnetic types, each offering distinct advantages for different tasks. Some of the factors to consider while selecting grippers include material property of components, material handling speed, cost and maintenance considerations, etc. Thank you.